Welcome. These series of videos are going to go over the start of Unit 2, which is our forces on dynamics. I'm going to be going through five separate videos to go over each of these. So the first video is just 2A, but the fifth video in our series of 5. We should be done with 2E. So keep these videos short and sweet to help, focus on the key points. So in this, we have a series of trials where Carlos and Dominique collect the following data from an experiment where they exerted the same force, F. So they're going to keep pushing with the same force value, or somehow exerting the same force on an object, but these objects have different sized masses, and this is actually something that we'll actually be doing in class eventually. So we'll go ahead and graph it. As you can see, masses on the x-axis, accelerations on the y, at 2, at 1.5, 0.3, 0.4, 0.5, 1, 2. There, at 4 is 0.75, 4 kilograms, 0.7, 0.75. At 5 kg, it's 0.6. At 7 kg, 6.7, 0.4. At 12 kg is 0.3, 11, 12, 0.3. Acceleration of 0.3 meters per second. Well, I apologize. At 15 kg, I have 0.2. And at 18 kg, 16, 17, 18, I have 0.15. Okay. Now, you can see, usually, we know it's linear if I have like this, constant slope. This is y is directly proportional to x, linear relationship. In other cases, we've dealt with y is proportional to a quadratic x squared. X, y. Because at 1 it's 1, at 2 it's 4, at 3 it goes up to 9. On a x squared relationship. This is a new type of curve. I'm not going to connect the dots because you just want to see the trends. It just says plot. It doesn't say to add a trend line. It doesn't say to connect the dots. We're just plotting. But I can see I don't have a linear relationship and I don't have an x squared relationship. It's almost like the backwards of an x squared relationship. So let's go and explore this data set. If we're looking at these, I'm going to choose some relationships, and this is a key point. The 4 main types of relationships. Y, in this case, y is proportional to x. Y is proportional to 1 over x. Y is proportional to x squared. And y is proportional to the square root of x. Or conversely stated, the square of y is proportional to x. If I squared y, then I just have x. That's another way of writing this one. Y squared is proportional to x. So I definitely think when looking at these 4 relationships that we need to be familiar with, this is the one that matches the graph data set. So based upon the graph from graph A, as mass increases, acceleration decreases. Therefore, acceleration, and this is just following this line side here, as x increases and y decreases, instead of x I place mass, instead of y I place acceleration, because that's exactly what's being graphed on the x and y axis. So in that case, I'm going to replace the x and y with the actual physical values. This is my x physical value, this is my y physical value. Therefore, I can kind of think of holding this statement true to just replacing my variables with the actual physical quantities, mass and acceleration. Let me zoom out a bit. I hope that works a little bit better for some folks. Therefore, acceleration is, if we look back at this guiding sentence, acceleration, which we said was y, is inversely proportional to x, and for us, x is mass. So acceleration is inversely proportional to mass. So, based on analysis in part B, what could be graphed instead of mass and acceleration that would lead to a linear relationship? Well, this goes back to some of the worksheets we were doing in Unit 1, the kinematics unit. We can actually graph mass versus 1 over acceleration. To get it to be linear, take all the acceleration values and divide 1 divided by each value will get us a different xy plot. Or conversely, you could have graphed 1 over mass versus acceleration. And we have made these slight adjustments in the data table, like creating a new column that was 1 over a, and then taking these values for a and doing 1 divided by them, you got some new values, and then plotted this 1 over a versus mass. Then it would come out to have been a direct linear relationship. With the slope being that constant force F. So what is the physical meaning of the slope in the linearized graph part C? Well, we think about it. If I had done this, I'm really rearranging the equation F equals m times a. But in our case, what's happening here is that for us, like we defined above, this would have been the x, this would have been the y. So if I was going to rewrite it as y equals mx plus or minus b format, I need the m and the a mass and acceleration to be separate from each other. So if I rewrote this, I would have force times 1 over m equals a, because I would have divided both sides by m. And so rewriting this in this format, I get a equals f times 1 over m plus or minus b. Now in this case, we see that, if there's no force, if there's no mass, there's no acceleration. So in this case, I can assume my y-intercept equals 0. And so I'm left with the equation a equals force times 1 over m. And then I can see some things match up. My y becomes my a. My x value, because now it's linear, is 1 over m. As stated, how do we make it linear? We identify the proportion. We identify if we did this, we will have it linear. If we did this, we will have it linear. If we did these relationships, it would be linear. Taking it after the fact, like what do we have? After the fact, if we adjust it. So in this case, this means that the last thing that's left over when I rewrite in the y equals mx plus b format is that what is the physical meaning of the slope? Well, the physical meaning of the slope is going to be the force. And that makes sense because the slope is not changing in the linear graph. If I had it linear and I was graphing it out, I would have this be acceleration here, the y-axis. This would have been 1 over mass, which is now my x-axis. And I would have had a linear line of data with the slope m equaling the force, and that's a constant slope. And that actually matches back to what it says, that they exerted the same exact force, F, on every object of different mass. And so your answer here is the slope represents the constant force exerted on the objects in this case. And so entirely what it would depend on is like what force were they using? Were they using 10 newtons, 100 newtons? And of course that would change the slope, but it would still be a constant slope, whatever the F it was. Maybe a greater force, maybe a lesser force, a mid-range force. I mean, the slope entirely depends on the actual value of F that was exerted on these objects. Okay, that's a little haphazard video. You can rewatch it, go backwards, or definitely post some questions that I can follow up on the YouTube page. Thank you, and moving on to the next video for the next question.